right, welcome to the really fun video. And we're going to start this video by talking about specifically how to approach the video, okay? So you do not need to memorize everything in this video. You do not need to learn everything in this video. We're going to introduce some very cool things. I'm going to tell you what you need to know and what you don't need to know. And just kind of, there's going to be one point in the video where I want you to just put your pencil down and enjoy the ride. All right, so without further ado, let's get into it. All right, so we're going to preface this by saying that ordinary differential equations are very old, okay? People have been solving ordinary differential equations for over 300 years, so it's always a little sad to me whenever I learn math and I go, man, this is really hard. Oh, people 300 years ago were solving this. What are people doing now? The answer is people are doing very, very complex mathematics right now. If differential equations is 300 years old, some of these techniques. Okay, so, you know, people over time and a lot of very smart people have spent a lot of smart time looking at a lot of these things. So that's a little preface. And then just a reminder that as we get into some different techniques for analytic techniques, by the end of this quarter, we're going to have a lot of different analytic techniques. You don't need to necessarily have them all memorized. You should have some memorized, and you should have all of them kind of in one page in your notes so you can reference, be like, oh, is this equation? Is this equation? And you should be able to kind of recognize the equation and use the appropriate method. That's really what I want you to kind of take away from this section. Now, if that preface hasn't terrified you, I don't know what will, but don't worry. This isn't going to be terrible. So we're going to start by telling you what a Bernoulli equation is. Later on, we'll tell you what a Riccati equation is. Not to be confused with ricotta, which is what I always think about. Anyway, a Bernoulli equation is just a differential equation of a certain form. All right? So a Bernoulli equation is an equation of the form dy dt equals some function of t times y plus some other function of t times y to the nth power. So you will notice here, this is not a linear equation. It's also not separable, right? Y is being raised to the nth power. Ugh, that's no good. It's also not autonomous unless these happen to be constant functions. But in general, it's not autonomous. So really, there's not that much we can do with this, with techniques that we've learned. But remember what appendix we're in. Is there some sort of substitution that can clean this up a little bit? Well, you ready for a magic trick? Because here's a magic trick. You don't need to know how to come up with this. But if you have a Bernoulli equation, try this substitution. Let z be y to the 1 minus n power. Again, this is n. Then what you're going to get is something a little interesting. I think I'm maybe not going to do this in generality. You could do this in generality, but we'll do one specific example. All right. And again, remembering to do all your substitutions. This is going to give you something really nice. I'll just kind of jump to the end. If you do a few steps, it's going to take a bit of math. You're going to get 1 minus n times r of t times z plus a of t. And what you'll notice is that this is a linear equation. Right? This is just a number, a function of t times just our dependent variable times some other function of t. So if we have a Bernoulli equation, which is not linear, we can do a substitution. It'll take a bit of work to get here. Not too much work. And then we have a linear equation. We can solve it using methods of 1 point something. All right. If we have constant coefficients, we can use some guessing methods for finding the particular solution of the non-homogeneous equation. Otherwise, we can try integrating factors if we have something nice. Anyway, so let's get to it. Oops, jumped ahead there. Let's do an example. So I want you to rewrite this as a linear equation. And we're not going to solve it here. Again, that's chapter 1 stuff. We'll spend the time doing new stuff here. But rewrite as a linear equation. And I want you to get some practice with this. We get dy dt equals y plus e to the negative 2t times y squared. Again, this is not linear. It has a y squared. Okay, integrating factors is not going to work the way that we taught integrating factors. And we really don't have a method to do anything with this yet. So pause the video, try to identify what your substitution has to be, and see if you can turn it into a linear equation using substitutions. So we know z needs to be y to the 1 minus n power. N here is 2. So it's 1 over y. It's going to be our substitution. So dz dt, what's that going to be if we ddt this? Remember your product rule, or sorry, your chain rule, and your power rule. Bring down the exponent, subtract an exponent, multiply by dy dt from the chain rule. And we get that dy dt is just negative y squared of this. Okay, so negative y squared dz dt is equal to dy dt. So when we do that, when we substitute everything in, what does our new differential equation become? It becomes negative y squared dz dt equals y plus e to the negative 2t times y squared. And again, this really isn't great. We don't want things with y. When we do a substitution, we want everything to be in the new variable. This is what we want. But let's clean it up a little bit. Multiply everything by y squared so we get the derivative by itself. And let's multiply it by negative y squared. When we do that, we get negative y cubed plus e to the negative 2t. Oh, sorry. Whew. I just got really scared there. Let's divide everything by negative y squared. I was like, this is not looking better. If we divide everything by negative y squared, we get something really nice. All right, both terms become negative. And then one of these y's cancels and both of these y's cancel. And why is this especially nice? Is because this is z. So we get our new differential equation dz dt equals negative z minus e to the negative 2t, which is pretty neat. All right, and we can solve this. All right, we can solve this as a constant coefficient, first order, linear, non-homogeneous differential equation. How's that for enough terms? Okay, so we can solve this, I believe, with either method. I'm not sure what the integral is going to look like for undetermined integrating factors. But yeah, again, if you want more practice, we're not going to do it here. Pause the video, solve it. I'll give you the solution. All right, the solution is z is equal to k e to the negative t plus e to the negative 2t. And we take that to substitute out and get our final solution. Y is 1 over that, right? So it's 1 over k e to the negative t plus e to the negative 2t. Okay, so that would be good, some good practice if you want more chapter 1 practice. And you can see how this original thing that we could not solve, we can solve it with a substitution. So here, I wanted you to rewrite it as a linear equation. So in this case, this really is where we would stop. That's how we could rewrite it as a linear equation. And again, if we were really being good math students, we would include our substitution with that z was y to the negative 1. That's an important part of our substitution. Okay, so that's a simple Bernoulli equation. That's how we can solve Bernoulli equations. And you might wonder, why do we care about Bernoulli equations? So for this next chunk, most probably for the rest of the video, I want you to put your pencil down, just kind of watch, listen, and just kind of try to absorb. Maybe jot down a couple things that might stand out to you, but you don't need to memorize this stuff, or really, it's more for like context and stuff. So that being said, I've written down some things. So why do we care about Bernoulli equations? So let's look at a typical differential equation that this is the first order differential equation that we always work with in this class, right? The derivative is just some function of t and y. Doesn't have to be linear, doesn't have to have constant coefficients, but it does have to be first order for what we're talking about right now. Because again, if you remember, a Bernoulli equation is first order here. Okay, so we can approximate the equation. We do that in both appendices. And now if you haven't taken Calc 3 yet, and Calc 3 is not a prerequisite, you may not have heard of Taylor series before. Maybe you have. But essentially, we can approximate a function. And again, we're not approximating the answer. We're approximating the equation by looking at the expansion of this right-hand side. And we can choose where we want this expansion centered at. We can center it at whatever C we want. Then we can approximate this right-hand side with a Taylor series. And that's what this is going to look like. So if you're curious about this, great. Otherwise, don't worry about it. What matters is that this is a polynomial, right? Here's a function of t. I should say it's a polynomial in terms of y. Here's a function of t plus another function of t times y plus another function of t times y squared plus another function of t times y cubed, and so on, infinitely many. All right, so this is just a function of t. Well, it's a function of t and y, right? But it's a polynomial function in terms of y, which is the important part. All right, so a lot of times when we're working with Taylor series, we don't look at infinitely many terms. Infinitely many terms is, to be quite honest, a lot of terms. So a lot of times what we'll do is we'll just look at a first order approximation. Maybe a second order approximation for differential equations, but really we can go as high as we want. So even though the original equation may not be linear, we can look at a linear approximation of the equation. So what we can do is we can say, well, we can make a first order approximation of our differential equation. And if we do that, we have dy dt equals r of t plus a of t times y. This is a linear equation. We have tools to deal with linear equations. It's an approximation of our original differential equation. So our answer, may or may not have any fidelity to the original answer that we may or may not know. But we could also look at a second order approximation, which is going to be better. And what does that second order approximation look like? dy dt is some function of t, specifically this function of t, plus some other function of t times y, this function of t times y, plus another function of t, which is also part of the Taylor series, times y squared. All right. And this is what's known as not a Bernoulli equation, right? It's only a Bernoulli equation if we don't have this. So what are we even talking about? I just asked you, why do we care about Bernoulli equations? And I'm answering with something that's not a Bernoulli equation, right? What kind of equation you think this might be? You guessed it. Why do we care about Bernoulli equations? One of the reasons, and again, there are multiple applications in physics and other aspects, but a ton in physics. One of the reasons we care about Bernoulli equations is because of Riccati equations. All right. This is an example of a Riccati equation, and we have no general way of solving these equations. There's no way of solving all Riccati equations. This is a Riccati equation of this form, basically quadratic, right? Okay. But what we can do with Riccati equations, and what we're not going to do in this video, is we can find, if we have any particular solution to this equation, and there are ways of kind of guessing and finding particular solutions to this equation. If we have any particular solution of this equation, we can use that solution, do a substitution, and our substitution is going to give us a Bernoulli equation, and we can solve that Bernoulli equation with another substitution, and then substitute back twice to get a solution to the Riccati equation, which is the second order approximation to our original differential equation. Isn't that neat? I'm not going to make you do that. But again, the point of this video is for context, like seeing the beauty of mathematics, seeing how things go together, and just giving you some general exposure to these things. So if you do hear in physics or do hear in another math class about Bernoulli equations or Riccati equations, it should at least jog your memory of like, oh yeah, we that's something to do with differential equations. There's something that we can do to work with them. And then of course you could, if you had to solve them, you could come back and you could find all the details and stuff like that. But here, just kind of going for exposure and some context and like trying to teach some general ways of approaching and problem solving these things. And the book addresses this in a bit of a silly way. And I'm actually going to show you an excerpt from the textbook right now. This is the last part of Appendix A in our textbook. This is avoiding depression. And basically what the textbook is talking about here is saying you don't need to have been able to come up with this, okay? People have been doing this for over 300 years, spent a lot of time, a lot of very, very smart people, right? Coming up with all these connections. What I want from you is to not be able to come up with this, but to recognize strategies, to practice working with those strategies and really kind of like associate and kind of build your foundation for mathematical skills. And so that's why we're talking about this. And then, yeah, if you have the method, I want you to be able to follow it, and I want you to be able to do that. But you certainly don't have to memorize most of the stuff in this appendix. Write some stuff down. You can use your notes and stuff like that. That's kind of what I'm really looking for from you for this. So don't get overwhelmed. I know it's a lot. Appendix B is also very cool. It's also kind of a lot. But then we'll finish Appendix B and go back to Chapter 2. All right, but this is a very natural place to put the appendices, right? Because it's talking about first order equations, which is what Chapter 1's all about. But anyway, fun stuff, cool stuff. Can be overwhelming, is definitely difficult. But yeah, hope you enjoyed learning about it a little bit. Next video, we'll talk about power series. And also, next video has one of the coolest graphs I've ever done in a math class. So you're going to be wowed. I guarantee your socks are getting, what? We'll save it for the next video. Bye-bye.